Yeah, welcome from my side. There are two things today I want to talk about. One is actually recent research results and some history on how I got to all this LSTM stuff. And the other thing will be how you can get your hands dirty and start reproducing or implementing and starting some of the stuff that I will present. I saw that there were a lot of talks on R in this series. So unfortunately, today we will be seeing some Python, not R. But I hope I can convince you that it shouldn't be too much effort for you to switch. OK, so the first thing, before I get started with the actual research part, I want to start with like a small introduction sync on the topic that I'm talking about, because I'm not sure on the background of everyone here. So to not assume anything, I would just give a very, very broad overview what kind of problem I was trying to solve when I started this kind of research. So the task at hand is rainfall runoff modeling, which means if you look at the map and you point to some river somewhere, what you want to do is to model the stream flow in this river, given the meteorological inputs of the upstream area that influence the amount of water in this river, right? So this is called rainfall runoff modeling. And as you can imagine, probably if you just look at naturalized basins, so even without human influence, the discharge in basins in different environments and places of the world look completely different. You have very spiky rivers that fall completely dry over extended periods in like arid basin and the arid regions in the desert, like here in the lower left in Arizona. You have very seasonal patterns in, for example, the Rocky Mountains, where you have very little discharge during the winter and then elevated discharge and peaks in the melting season. And you have like a huge diversity of signals and hydrographs that are controlled by different processes that are important in all of these catchments. And now the thing is that if you want to model all of these rivers, your model needs to implement all of the important processes that control the discharge in these rivers. By the way, I see that everybody has their video off. I would be very happy if some of you can turn the video on so I can see some faces and I'm not speaking into the void. And I'm also open to questions. So also feel free to interrupt me if there's anything that you want to ask immediately, right? Otherwise, we will have a long time for discussion at the end. OK, amazing. So going forward, there's like a ton of hydrology models that have been implemented over the past, let's say, decades or even centuries. And most of these hydrology models are kind of Buckettype models, right, that conceptualize some of the processes that happen in the real world into actually really just a bucket, right? There's a bucket that stores soil moisture. There's a bucket that stores snow. You fill these buckets and you have fixed equations, how these different buckets interact with each other. And there's like a handful of parameters that like control the size of the buckets or the flow rates between these buckets and so on. Yeah, I might make myself a bit unpopular, like here at the very beginning, if I say that over the past few decades, probably not too much has happened in this kind of research. And operationally, in many places of the world, we are still using models that have been implemented in the 70s or 80s of the last century. And all of these models have in common that they are driven by meteorological forcings, mainly temperature and rainfall, sometimes PET. And then they have to model the entire system. So all of the processes that happen in the catchment and that lead to the final discharge, right? And then on the state of these models, like if we look performance-wise, we see the following. And here it's worth to say that in general, I would say there are two completely different ways how you can calibrate these models, like to get the best possible parameters of your model for a specific basin. One approach is you calibrate the model parameters individually for each of the basin that you are interested in. This is called single basin modeling or single basin calibration or whatever. And the other approach is regional calibration. So here you have a second model, let's say a meta model, and you basically train this model given some auxiliary data like catchment attributes, soil properties, land cover attributes, to give you, given these attributes, the parameters of this model, right? The benefit of such an approach is that you potentially could apply this model to any place on Earth because you only need this usually globally available catchment attributes that you can then feed into your meta model to get your model parameters. However, the reality is that if we compare both of these approaches on the same basins, and I think this is true for all our hydrology models, at least that I'm aware of, usually the per basin calibrated hydrology model is much better than the regional calibrated counterpart, right? So here, what you can see, and we will see a couple of these plots, so let's spend some time looking at it. You see the cumulative density function of the NSE on the x-axis of two different hydrology models. Both were calibrated on the same sets of basins with the same forcings and the same periods. Once calibrated for each basin individually, which is the dashed line, and once on with a regionalization approach, which is the solid line. And so for CDF plots, usually the further, like for the NSE, the further lines to the right, the better the model. And what you can see here is if you, for example, draw a line at 0.5, this would, the intersection now marks the median. You see that the single basin calibrated hydrology model is always substantially better than the same model being calibrated with the regional model approach. And I think this will be no surprise for everyone that played around with regional models and this kind of approaches. So the question is, why is regional modeling important, right? So regional modeling is important for a couple of reasons. One is that there's just a lot of regions in the world where we don't have observations. We can't calibrate a model for any river in the world because we don't have historic observations everywhere. And the situation is going to get worse because even where we once had stations, the state of the stations is declining and we're actually getting less and less data. And this is specifically the case in low income and developing countries where some of the most severe floods are happening. So where we actually want to have models to be able to provide good flood warnings. And this brings me, skip the slide actually. So this brings me to my second point. We want to have regional models because flood forecasting, and this is linking to my work at Google, like the most severe floods are taking places in low income and developing countries. They causes hundreds of millions of billions of dollars of damage every year. A huge number of people are dying every year from flood. And one of the reasons is that like many of these places just don't even have any kind of flood warnings at all, right? I think in the pre-meeting, Stefan mentioned that 70% of the people being affected by flood. When I started actually my whole line of research, I was a master's student in hydrology, but for a project that I was working on, I was learning deep learning, machine learning. There's like amazing online resources that anybody can basically use to learn about this field. So I was studying machine learning, and one thing that pops up all the time is that getting worse with more data available to a model is actually the opposite of what we see with machine learning, where the more data you have, the better your model gets, right? And in hydrology, if we like think about it, it's actually the other way around. If we train one model, meaning the meta model and the hydrology model combined, right, with the regional modeling scheme, we actually get worse than if we would only look at a very tiny subset of all available data to train to a particular basin. So I was wondering, is there a way how we can use some approaches from deep learning with the available data that we have in hydrology? Because if we look globally and not at individual basins, if we are trading space for time, we actually have quite a lot of data available. So can we use this to get better hydrology simulations? So this talk is about LSTMs. And the reason why I initially thought that LSTMs is like a good fit of all available model architectures to try is the following. Hydrology models can mathematically be formulated as a state model, right? They have internal states like soils, moisture, and snow, and all this kind of stuff. And the states of the current time step are a function of the inputs of the current time step and the previous states, like of the previous time step. And I'm already sorry, like this is the only slide with equations that you're going to see. So this is all math that we will cover. And some model parameters, and then the output of the model is a function of the states and some more model parameters, right? This is like a very general formulation of a hydrology, of a conceptual state hydrology model. And the LSTM actually can be formulated in exactly the same way. The LSTM is also a state model. It has internal states, just as a conceptual hydrology model. The states are updated as a function of the previous states and the current inputs, exactly the same. And the output of the LSTM is also a function of the current states. And the LSTM also has some model parameters that we train during the model training, right? The big difference, though, is that hydrology models can only model processes that we, as the model developers, hard code into the model code, while the LSTM is able to learn any process that is important for the problem and that can be extracted from the data, right? It cannot learn anything that is not in the data, but anything that is in the data and that is important for the problem, the LSTM is able to learn it, right? If we like in a hydrology model, how many models are there that we use operationally that like are applied to forests and have interception included, right? None, like none of the operational models, not none, but very few. If interception would be possible, like important and deducible from data, the LSTM could learn it, right? It's the same model. It's just a very general formulation that potentially can learn any process. And now, going one step back and already like taking the results from all of my research, the LSTM applied to hydrology actually reverses the trend, right? And this is basically the outcome of many years of research. If you train a single LSTM on hundreds of data from on hundreds of data of hundreds of basins, a single LSTM, right? This model is substantially better than if you would train a single LSTM to every basin individually. So here we are getting better with more data. This is interesting for a couple of reasons, because for a long time in hydrology, and maybe it's still the belief, there was a question if we have catchment scale relevant theories. If there are any laws, any theories that we can learn in one basin that can be applied and transferred to a different basin. I would say some results of what I will show and present hints towards the direction that we have scale relevant theories, that there is something that we can learn in one basin that helps us get better in a different basin. And we were probably just not able with conceptual models for the moment to find these kind of scale relevant theories, but it seems like there is something, right? A correct flexible model applied to this problem is able to generate a benefit by looking on different basins than the basin itself. Now, how does it work? So you need, okay, so how does it work? Right, we're here. So you need basins, many basins. Potentially what many is still not clearly defined, right? We have a paper where we applied this approach to a benchmarking competition with like 100 training basins. And we got like the LSTM outperformed all other models. So like the trend of getting this kind of good models does not mean you need thousands of basins. I don't know if it's enough to have 10 or 15 or 20. It's a good research paper if anyone wants to do research on this and has compute. The third ingredient is catchment attributes, and this is really important. I will show on the next slide why. And it's actually the same that the same kind of data that we use in any regionalization scheme for hydrology models, right? I mean, we can be more flexible on what kind of time series features we use and what kind of catchment attributes we use with deep learning models, because we don't need to predefine how some feature influences the entire process. But in general, it's the same kind of features. We don't use discharge as input, right? It's similarly a full simulation model that only uses meteorological forcings. So why are the catchment attributes important? I really like to show off this video that I found on the internet. Unfortunately, I don't know the source. Amazing. Okay, so in case it's not rendering, I will just explain what we are about to see. So you see two plots, two blue boxes, and these two blue boxes stand for two catchments, right? And these two catchments, try to reload the slide. Let's see if it's will come up. Oh, it seems like that. Okay, so these two boxes stand for two catchments with the same size, the same slope, two catchments that are very similar in shape and everything. And they get the same amount of meteorological forcings applied, right? They have the same room temperature and they get like water through watering cans. The only difference is that one of these boxes has like plants growing in it. I don't know what's happening. Okay. One has plants, the other one has bare soil. And then what you can see is that the response from these two boxes is completely different. The left box without the plants will immediately drain all the water through the upper tube in like very muddy and dirty water, while the other one has like a long buffer through the root system of the plants, and then like substantially later than the left box starts to drain very clear water from the lower tube, right? And if you have a model that tries to, I will just go back and we can see the preview. Yeah, if you want to have a model, right, that wants to model both of these boxes at the same time, then the only way how the model does know that the same meteorological time series produce a different discharge signal is if you tell the model about the catchment attributes, right? That's the only way how the model can learn this. So this why catchment attributes are really important. There are still some papers that try to do the same approach, but without catchment attributes, and then you're substantially worse with the LSTM. So how does it compare to hydrology models? There were some early on benchmarkings on the Chemnitz data set, like a large sample hydrology data set from catchments in the US. And there were a couple of groups that calibrated their models. Most of them are the model developers themselves. On the same set of basins, the same periods, and using the same forcings. There are multiple forcings in this data set. And so the left-hand side of this plot now compares the LSTM to the regional hydrology models. So the models that we have seen initially already, right? And this is actually the fair comparison because the LSTM is also a regional model if you want so. And again, this is the CDF plot. So the further lines to the right, the better. And the right-hand side of this plot now compares the LSTM to per catchment calibrated hydrology models. So all of these models were calibrated on each basin individually. In some cases, I think the HBV model is actually not one model, but an ensemble of 100 calibrated HBV models per catchment, right? So this is like in the range of the best we can do with these kinds of hydrology models. And then you have the LSTM, a single LSTM trained on all of these basins together, and it's substantially better than these hydrology models. So the critique that I got when I published these results, or also like communicated these results the first times on the internet, was that, well, your model is just not generalizing. It's overfitting to the training data. It's not able to learn anything that's useful outside of these basins. So the natural test was to test the same model on ungauged basins, right? To train this model on a fraction of all basins and evaluate on a holdout basin set. And we did exactly this for the same setting in camels. But I would show different results from a more recent study, which is the Great Lakes Runoff Intercomparison project from Juliane May in Waterloo. Because this intercomparison project had one task, which was modeling PUB. But for the first time, also all hydrology models against which we benchmarked had to predict PUB. Because previously we were comparing the LSTM PUB versus calibrated hydrology models, which is like a very asymmetric comparison. So this now is a CDF.
Frederik, can I just ask what PUB is?
Sorry.
For those of us who aren't hydrologists.
Yeah. No. PUB is prediction ungauged basins. So it means how good is your model if you apply it to a basin for which you don't have calibration data, right?
Thanks.
So this is like kind of the holy grail, maybe. It's and for us at Google, for example, it's one of the most important things, right? Because we want to apply our model to regions that are flood affected, but where we don't have data to calibrate a model. So this is what you see. Again, the dashed lines are different hydrology models that are actually calibrated on a different basin set for each basin individually. And then to participate in this challenge, they made like a donor basin approach. So they just took spatially the closest basin, took the model parameters from this basin and applied it to the ungauged basin, which has limitations. And the solid lines are regional hydrology models. Again, models that potentially could be applied to any basin in the way how they are calibrated. You see that in this setting, it seems that even the per basin hydrology models with the donor basin approach are better than the regional hydrology models. But the LSTM, then again, it's like substantially better than this bulk of hydrology models. Yeah, so now I want to come back to the question, Nick, that you asked. If it would be sufficient if we have more data from a single basin, or if we always should train on multiple basins, right? And I posted this meme a while ago on Twitter. There's strong evidence that you should never train a LSTM for a single basin. And that's very important, even if you're interested just in a single basin, right? Even if you only want to model a single basin, there's strong evidence that you should not train your LSTM on just this basin. And to highlight why, one reason, this very extreme example. So assume we take a basin, or we take a lot of basins, and we split the data differently. We don't split the data with a usual temporal split into training and validation data, but we split the data based on return periods of the annual peak. Every year where the maximum annual peak is below a 5-year return period is a year that we use for training. Every year where the maximum annual peak is above a 5-year return period is a test year. So the orange years here are the training years for this particular basin. Green years are test years. We added some buffer around the test years that we made sure that there's no data leakage across the different training and validation sets. And the gray dashed line for this particular basin is the 5-year return period. So if you train a single basin LSTM on this data, this is what you will see, right? And the orange now, like the blue is the observation in the background. The orange is the simulation on the training data. So and for LSTM senses, it's always like you should get very good on this kind of data. It's the training data. This is the simulation that the model after training predicts for the training period. And green is what the model predicts for the validation years. And dashed line, something different now. It's the maximum value the LSTM was able to predict on all of the training years. And what you see is actually no surprise. It's something that hydrologists often raise as a concern, which is machine learning models are not able to extrapolate, right? No validation peak, not a single time step. It's not a single time step, actually. There are maybe some, but you are not able to get substantially above the threshold that you are learned during training. Now, if you look at the regional calibrated model trained on the same data split, you actually see this, right? Your model is able to predict higher values in the validation years of this basin than it has ever seen during the training period in this basin, right? And the reason is that it has seen higher values. It has seen higher values in different basins. What is an HQ5 in one basin in like the amount of water is not an HQ5 in a different basin. Your model has seen higher, more diverse data during the training. So LSTMs have saturation functions, right? Some of the activation functions inside this model architecture are these kind of saturation sigmoid functions or TAN-H functions. These functions were now optimized to a much wider set of values. You don't reach this kind of saturation behavior of the model in most of your basins. Now, the caveat is you will still see a saturation effect in the basin with the absolute highest values in your training set. But for everything else, like everything where your discharge is well below anything that you've seen during training as like the max peaks, you don't have any saturations. You are perfectly able to extrapolate in individual basins. And there's a paper actually already published by Jonathan Frame, who compares the LSTM on exactly this task to a Sacramento soil moisture accounting model like the old US National Water Model and the current US National Water Model. And the LSTM is actually able to better predict flood peaks, return periods, than any of these hydrology models. And here we can see the same kind of plot that he did in his paper, but just for the single basin LSTM and the regional calibrated LSTM in blue, single basin LSTM in orange. So these arrow bars that you are seeing here now is the absolute peak bias. So only looking at the peak, the annual peak. And the first column is the training years. It's every peak that is smaller than HQ5. And then the different bars are binned by like return period 5 to 25 and so on and so on. And you can see that the regional LSTM is consistently better in predicting unprecedented events in every basin than the single basin calibrated counterpart, which is because of the saturation effect, right? And now, Nick, coming back to your question, it's not finally answered. I still don't know. There are some experiments I'm currently running where we try to simulate this. To my understanding at the moment, it's much more important to have a diverse training set in the sense of having diverse discharge data of different magnitudes than having much more data from a single basin, right? Because at some point you will always end up saturating for this one basin. And but if you mix together a lot of basins, you will not reach this point. And yeah, just an anecdote. So our training set at Google contains like thousands of basins, and I wanted to see like where our model is saturating. And we are training on catchment area normalized discharge, right? So this is not cubic meters per second. It's this, like it's the volumetric unit divided by the catchment area. You get something like millimeters per day, which is more comparable across basins. You can train a model on very small and very large basins together and have like a more homogeneous set of discharge. And we have, and I'd say 98% of our basins have absolute maximum peaks below 100 millimeters per day. And then we have one basin with a peak above 400, a single time step above 400, and I think 5 between 200 and 300. And these, in total, 5 peaks led to our saturation threshold being above 200, actually, which means that for all our 99% of the basins that never seen something above 100 millimeters per day, we will never see a saturation. Like, we probably see a saturation if they would have a very rare event, but we could predict in this basin still up to like twice as much as they've ever seen, right? So it's very important for me. This problem, it's still there, the saturation. It's just happening at the very upper bound of your training data, but it will always be a problem if you train a single basin LSTM. Always be a problem, right? Just, and one other thing, why I want to highlight why regional model training is important, even if you're just interested in a single basin. So I picked now one paper, and I don't want to mention the authors because I think it's not their fault. I was the reviewer of this paper, and what they basically did was to compare the GR4H on hourly discharge prediction to LSTM and GRU on hourly discharge prediction. And their setup was they trained these models individually for 6 different basins. And they wanted to test the effect of available training data and how this affects, like, they had a fixed set of validation years and they varied the amount of training years, right? So the x-axis is the amount of training years they used. And they did like a sliding window approach. So they trained on all possible 1-year slices, on all possible 2-year slices, and so on and so on. And the outcome of their paper was, well, the LSTM, I'm now over dramatizing, the LSTM is not suitable for hourly prediction, and you should use the GR4J, GR4H. And I don't want to say like which model to pick. I just want to say, if you set up the LSTM differently for this specific experiment, the results will completely change. So what I did was, because I had access to the same data, they use publicly available data, and I have code that allows me to easily do this kinds of experiments. I trained this also 6 camel basins, by the way. So I took all the camel basins that we usually use for training and removed this 6 basins. So I never used any training sample of these 6 basins. And then I trained an LSTM on hourly predictions. And without using a single year of a single sample of these 6 basins, so the LSTM predicting PUP ungauged, the LSTM was better in 4 out of 6 basins than the best performance they had with the GRU model using all training data. Using a single year of training data from any of these 6 catchments, and then fine-tuning, which is take your pre-trained LSTM model that you trained on all of these hundreds of basins, and now continue training with a very few time steps and lower learning rate just on this basin. With a 1 year, like 1 year of data, in 6 out of 6 basins, the LSTM was better than what they reported for the GR4H, right? And now, from the operational side, I asked you, what's the result, right? Because I want to know not how good can I get with a very unrealistic setting for a model that should not be applied in this fashion. Right, was there a question? No, okay. I think that the question is, how good can you get with a model given the optimal setup for each model individually? And for GR4H, the best setup is to train the model individually to all basins. I would also not now compare an LSTM that I train regionally to a GR4H that I train regionally, because that's unfair to the GR4H. But similarly, the LSTM, if you train it regionally, will give you completely different results. So if I want you to remember one thing from today's talk, it's always consider training your LSTM on single base, not on single basins, sorry, oh, that's a Freudscher Versprecher, on multiple basins, the regional approach. Has to happen. Okay, so there's a couple of things that now follow this, and I will not skip them, but I'm happy to talk about any of this in the Q&A. There's papers that we released afterwards, how you can like do the uncertainty prediction that I already mentioned, how you can do data assimilation with LSTMs, how you can actually look what the model learned internally, because the LSTM is actually not a black box. It's I would say fairly easy to inspect what state processes the LSTM learns over time, and then we can look if this matches soil moisture or snow. Does it learn anything that we can identify as a physical process? And also the LSTM is extremely good in learning synergy from different precipitation products. So usually for every area on the world, you have more than one gridded precipitation product. And with any hydrology model, you can just use usually one precipitation input, which we know that there's not one perfect precipitation product. So the LSTM, as it's a machine learning model, you can just provide it 4 different precipitation inputs, right? You can just ERA5, DAMET, Maura, and ELDAS provide 4 different precipitation products from 4 different sources and provide it to the LSTM. And actually, we could show that the LSTM not only gets much better performance, but it's dynamically learning on which time step in which region to pay attention to which data set. Yeah, so there's a blog here linked below where we list all of these publications. And again, if you have any questions, we can also talk to the Q&A. The last thing I want to highlight now, and I will ask to include this in my talk, is how you can get started. And it's actually, okay, this is like a disclaimer. I will present now an open source software package that I developed. So it's not, I'm biased. So a few years ago, me and 2 of my colleagues, we published our research library. So all of our papers that we published ever was done with this code base, and we used this already internally for quite a while. And this code base is designed to be super flexible for the research purpose, right? For testing, quickly testing a new model, quickly testing a new data set or whatever. So if I do a review and I see something like, oh, they do like a setup with LSTMs on this data set that I have available, it takes me literally 15 minutes to start the experiment reproducing the results. So this is the Python library. I know many of you are probably more familiar with R. This library comes with full documentation that is also hosted online. It comes with installation guides. It comes with how do you set up a Python environment to get started. It is really aimed at, I would say, the entire library is aimed at hydrologists that don't have a lot of experience with programming, and actually you don't have to have any experience with machine learning. Actually, with this library, you are able to train a state-of-the-art LSTM model without writing a single line of code. So there's installation setups, how you do this. There are 2 different kinds of installation setups, one just for the user, and then there's one if you want to change something on the code, like if you want to implement a different model, add some data set support or whatever. And then we also have a couple of tutorials. So these are code tutorials like Jupyter notebooks that are step-by-step explanations with a lot of text, how you can do different stuff, how you can add a new model to the library, how you can add support for a new data set to this library, how can I inspect the internals of LSTMs, all this kind of stuff. We have tutorials there. And yeah, so I want to give you like a very quick overview what's like the main ideas behind this Python library. So the first thing is the central piece of any experiments is a config file, and this config file is a .yaml file. And you can define an entire experiment with everything that is implemented in NeuralHydrology. And I don't know, we have like, I think, support for currently for 10 or 12 different deep learning models. And we also have, I think, data loading functions for all chemins data sets and some other data sets. You can train any model on any of these data sets without touching a single line of code, just by defining this .yaml text file, which you can do with a text editor. But so there you define stuff like on which basin you want to train, what's the data period, what are the input features, what is the target, what's the loss function, all this kind of stuff is defined in this kind of function files. And then a very key central piece of this library is that Python is an object-oriented programming language, and we build very strongly on this paradigm and have a very strong class inheritance in all of this. And what this means for you is that if you want to add support for a new data set, for example, you have your new data set for basins in Germany, which currently is not, we don't have support for any public data set there. So the only thing that you need to do is take this template file, which is also included in the library, and you need to implement two functions, like a load basin data function that reads the CSV file and outputs a data frame. There's a clear documentation here what you need to do, and another function that loads catchment attributes, right? And then because you inherit from our base data set, this will immediately allow you to run experiments with this data set for various different applications. For example, all our data set can be resampled to different temporal resolutions, or you can, I don't know, sub-select features. You have all these sanity checks that your inputs are correct and all this kind of stuff. And then, right, yeah, okay, sorry, that was the next slide. And then the next point is that the library is written to be very modular in the sense that if you ever want to add a model or add a data set or add a new loss function or add whatever, you only need to touch two parts of the code, which is one implementing, for example, the dataset class on the last slide. And the other one is we have all these kinds of get dataset, get model, get loss functions that, given one of the config argument that you define in the YAML, it will return the correct object, right? And that's the only thing where you now need to add another elif. You add your new data set, and immediately you can train any model that's implemented in the library on this data set. Okay, I don't know here, something happened with my animations. Then you can train your model on two different ways. You can either, we have an API from the command line, so you can just train the model without opening a Python file and starting a Python file, just pointing to the YAML file that defines the experiment, or you can integrate everything into a larger Python script and also call our Python API. And the last thing is we also have support if you have access to a cluster, how you can easily set up experiments that run on multiple GPUs and all this kind of stuff is already implemented. And this library is actually used by us internally at Google. We don't use this library, but we use a port optimized for Google infrastructure. But this library is used by various research groups. And I know NASA is using it and some companies are using it. So yeah, if you're looking forward to test some things around LSTM and you have no experience how to start, give NeuralHydrology a try and leave us to quickly mention. I will just make it one thing. I wanted to mention that I think 2 weeks ago, Google officially announced what is called the FloodHub, which is now publicly available and will be populated with more and more rivers in the world. So this is the dashboard that Google provides to external users to get flood warnings. This is connected to Google Search and Google whatever. So if you're in a flood-affected area, you search something on Google Search, you would get a warning. This is how we alert in all of India, not added here at the moment, but India is almost completely covered. So we have India, Bangladesh, Brazil, and Colombia as direct partner countries. And now, basically using the approach that I presented today, we have now a model that we can apply to any river in the world. And we are now, like we made an initial launch of, I don't know, 150 or something rivers, but over the next months, we will add more and more. So Google, the g.co FloodHub, this is how we communicate discharge. And this is still very beta. So we are happy to get any feedback and wishes and whatever. So I think there's a lot of work here. And then the last thing, just contact me if you have any question that was not answered today. I'm happy to. I will be at AGU next week. So if anyone is in Chicago at the next week at the AGU, feel free to reach out if you want to have a coffee